Yeah, student, our today's topic is magnetic field due to a straight current carrying wire at any point. So, here is a point whose distance from this wire is a small a, and we want to calculate the magnetic field at this point due to this whole wire. For this, what we will do, we will easily apply the Biot-Savart law for this point, and we have the formula which we have discussed earlier in last video, that the magnetic field due to a straight current carrying wire is mu naught by 4 pi I dl sine theta by r square. That was the Biot-Savart law. That was the for a small current carrying element. But in this lecture we will learn the magnetic field due to this whole wire at this point. For this, what we will do, we will again consider a small current carrying element here. Again we will consider a small current carrying element here whose length is, let's say, dl, and we will join this dl to this point, then this angle will be theta, and we will join the end of this wire from this point, end of the wire to this point, and also to this point. So let's say we will get an angle here. This angle is, let's say, phi 1, and another angle is, let's say, phi 2. Another angle is phi 2, and the angle which is formed between these 2 points is, let's say, phi. And we want to calculate the total magnetic field at this point. So we have the formula for the small current carrying element, that is dB, and this dB is equal to what? So this dB is basically equal to mu naught by 4 pi I dl sine theta upon r square. If you want to calculate the magnetic field due to this whole wire, we will easily integrate this term, and we will get the integration of dB will be equal to b, and that will be equal to what? So mu naught by 4 pi, and I is constant, and the remaining term, that is dl sine theta upon r square, is variable. So to integrate this whole term, we must convert this whole variable into a single variable so that we can easily integrate this term. Our target is to convert this whole variable into a single variable, and that single variable will be equal to phi, will be basically phi. And how we will convert this whole variables into the term of phi? Let's see the distance between this dl and this point is, let's say, l, and we can see from the figure this angle is 90 degree. This angle is 90 degree. So we can say sine theta is equal to what? So sine theta can be easily written as sine, here is the theta, so sine theta can be written as sine 90 minus phi, and this sine 90 minus phi will be equal to what? Cos phi. So we can convert this theta into the term of phi easily. Another variable is r. So this distance is basically r. The distance between dl and this point is basically r, and we want to convert this r into the term of phi, and the another constant, that is a small a, which will be always constant. It will not depend on the length of the dl or the position of the dl. This perpendicular distance will be fixed for this point and this conductor. How we will convert this small r? So we can easily apply the formula of cos here, and we can write cos phi is equal to a upon r, or we can say a is equal to, sorry, we want to calculate the r basically, right? We want to calculate r, so we can say r is equal to, we can say a upon cos phi, and this will be equal to what? A sec phi. This will be basically r, that r is nothing but a sec phi. And another remaining term is what? So another term is dl. So we can see this distance is l, and when we apply the formula of tan phi, this tan phi will be equal to what? This tan phi will be equal to L upon A, or we can say L is equal to A tan phi. When we will differentiate this with the respect of d phi, then we will get dl of d phi will be equal to a is constant, and the differentiation of tan phi with respect to phi will be equal to what? Will be basically sec square phi, or we can say dl is equal to a sec square phi into d phi. This will be the value of dl. So we have first equation this, and second equation this, and this is our third equation, and this is our fourth equation. Now we will put this second, third and fourth equation in equation first. What we'll do, we will put first, sorry, we will put second, third and fourth in first. So what we will find, we will find b is equal to mu naught I upon 4 pi integration of, at the place of dl we will put what? We will put a sec square phi into d phi. At the place of sine theta we will put what? We will put cos phi. And the place of r we will put a sec phi, and here is r square basically. So if here is r square, so we will put a sec phi at the place of r, so we will get basically a square sec square phi. This sec square phi and sec square phi will cancel each other, and this a will cancel a square. Then we will get what? We will get b is equal to mu naught I by 4 pi integration of cos phi d phi, and the limit of this phi will be equal to what? From where to where? This phi 2 is anti-clockwise and this phi 1 is basically clockwise. So we will put here what? We will put here minus phi 1 to phi 2. Now this b will be equal to what? This b will be equal to mu naught I by, and here a is also remaining, sorry, mu naught I by 4 pi a, and integration of cos phi will be equal to sin phi, and its limit is minus phi 1 to phi 2. Now this b will be equal to what? So this b will be equal to mu naught I by 4 pi a sin phi 2 minus sin phi 1, because sine of minus phi 1 will be equal to minus of sin phi 1. So this will be what? This will be, how we will put here, basically sine of minus phi 1, sine of minus phi 1 will be equal to minus of sin phi 1. So mu naught I by 4 pi a, and this will be how much? This will be sin phi 2 plus sin phi 1. This is the total magnetic field at a distance a from a wire whose end angle is basically phi 1 or phi 2. Now this equation can also be written as in the term of this and this equation. Let's say this angle is alpha and this angle is beta. So if we'll put here, we can easily see sine of phi 1 will be equal to sine of phi 1 will be equal to sine of 90 minus alpha, that can be written as cos alpha, and similarly sine of phi 2 will be equal to what? Cos beta. So we can write this equation in such a way that b is equal to mu naught I by 4 pi a and this will be cos of beta plus cos of alpha. It can be write like this. This is our final equation. Okay, now there will be some case. What? Case 1. Case 1. What will be the case? If wire is too long, wire is too long, and point of consideration is at mid of the wire. Mid of the wire. What is the question? What is the case saying? That is, this is a too long wire. Too long wire, and here we want to calculate the magnetic field. This distance is a. When we'll increase the length, let's say here is the length and here is the a distance, and this is the, let's say, phi 1 angle. When we'll increase this length, this angle will increases. When or increase, then this angle will also increases more. And this, when we will increase this length up to infinite, then this angle will tends to 90 degree. So in that case our phi 1, in that case our phi 1 and phi 2 will be equal to 90 degree, and so our total magnetic field at this formula, at this point, will be mu naught I by 4 pi a sine 90 plus sine 90. We will get what? B is equal to mu naught I by 4 pi a, and sine 90 plus sine 90, that is 1 plus 1, that will be basically 2, and we will cancel this 2, this 4 by 2, and we will get B is equal to mu naught into I by 2 pi a. This is the final formula for long wire. Now if point of consideration is at any end, second case, case 2, what if point of consideration is at any one end of long wire. That is, this is a long wire and we want to calculate magnetic field at this point or at this point, any end of the wire. In that case, our one angle phi 1 will be equal to 0 degree, and or phi 2 will be 0 degree, any one will be 0, and another will be 90 degree. Then our value or formula of magnetic field will be mu naught I by 4 pi a and sine 90 plus sine 0. This will be sine 90 plus sine 0, or we can say B is equal to mu naught I by 4 pi a. The another thing is that if we want to calculate the magnetic field, let's say this is a wire and we want to calculate the magnetic field in front of this wire, here or here. So at this 2 point, magnetic field B will be equal to 0. Why? The reason is that if we want to calculate the magnetic field at this point, we will consider a small current carrying element dl, and we will join this dl with this point, that is basically r, and the angle between this r and dl will be 0 degree. That means theta will be equal to basically what? Theta will be equal to basically 0 degree, and we know the small current carrying element's magnetic field dB is equal to mu naught I by 4 pi a, mu naught I dl sine theta, I dl sine theta Where sine theta, oh shit, mu naught by 4 pi ideal sine theta by r square. So for this 2 point our theta will be 0, so dB will be 0, and if dB is 0 then whole magnetic field will be 0. Okay, so our topic is only up to this point. We will discuss in the next section about the magnetic field due to a current carrying circular loop. Thank you so